This meeting is being recorded.
Okay, hello everybody. Welcome back to I'm sure everybody is disappointed, distraught that your Thanksgiving break is over. I know. But the good news is that we get to do data mining today. And so yeah, it's good for me to see you all. Hopefully it is at least good-ish for you all to see me. Today in class, last time in class, we were talking about our last notes packet in our overfitting folder over here, this notes-validation. We'll get to that in a little bit, finish that up probably today. But before doing that, I want us to talk a little bit more about the final exam. And so there's a new folder, final, in our repository here that has all the details for the final exam. And we will spend most of this week preparing you all for the exam here. There's three Python files in here, three important files. This learning pipeline.py file is the most important of those. This is going to be the outline of your final exam here. And then this example 1 and example 2 are just two variations on this file right here that we will show exactly what the the style of problem will be. So we'll be talking about all three of these today. And then after we talk about these, we'll switch back over to talking more about this last set of notes. And that'll be everything for today. Couple of administrative things here before we get into the nitty-gritty is that, so my availability this week is there'll be the standard office hours of tomorrow, Tuesday, 9 to 11 a.m. Hope to see many of you there. The Friday office hours is also during the capstone presentation for the data science major here. So I'm not available for that. But we will have dedicated review sessions, several of them this week, besides what we're doing in class here. So my suggested times here are Thursday, 9 to 11 a.m. and Friday, 1 to 3 p.m. But if for whatever reason these times don't work for a lot of people, you all can feel free to suggest alternatives and I'll try to make them work. So that's one important administrative thing for us to talk about today. There's also there will be some extra credit homework assignment this week that goes along with the final exam. So we'll talk about that as we talk about this learning pipeline.py file right here. And then as a reminder, there was a homework assignment due last night. I saw lots of submissions for them. I haven't fully graded it yet, but if you are, there's still a handful of people who haven't submitted it. If you're one of those people, then please submit it before the late penalty catches up to you too much. Any questions about anything administrative? Everyone's sad. It's the last week, of course. Classes. Obviously, this class you want more of, but your other classes too. Just sad to see it over. Sad that break's coming up.
Darn.
Oh, darn. Okay, well then let's break that sadness and get right into some details here. So your exact final exam format here. Exam, again, worth 128 points, 2 to the 7th points. So far, we've had 156 points in this class, and so that's will be a little bit less than 50% of your grade, the final exam here. The initial problem, and again, too, another thing I didn't write right here, but the final exam will replace any of your lower grades in, say, midterms or quizzes. And so if you do really well on the final exam, then you can get an excellent grade in the class. Certainly possible for anybody in this class to still get an A coming out of the class if you do well on the final exam here. Okay, but so the initial problem on the exam, you'll be starting off, I will give you some variation of this learning pipeline.py file. And so let's come over, switch my screen here in a second to talk about this Python file. have it opened up right here. And again, this file comes from this learningpipeline.py right here. And we'll just walk through at a high level what this file is doing and how it will be related to your exam here. I don't have, unfortunately, printouts of this file for anybody who normally likes printouts because of the power outage. It means the printer still not working, but hopefully it's not as critical to take notes on this. But still, I'll be saying things that aren't written down anywhere, so there might be some things useful for taking notes. I have this file broken up into 6 different steps that are labeled like this, step whatever, and then what that step is doing. So this first one, not very important, just loading a whole bunch of libraries right here. And then step 1 here is a little bit more interesting. It's what's going to be originally loading our data set. And so what I have being loaded right now is this German credit data set. It's a famous data set for predicting whether somebody's going to default or not default on a loan. It comes from a German bank, and it's I don't know, fairly old now, about 30, 40-ish years old. But it is still widely used by banks, and in particular, we've used this in several practicum projects, either with the data science capstone or with the fintech practicum. And the reason for this is because, well, it is accessible, so it's easy to load in on these libraries and get right to the interesting stuff. But it also has the same exact format and content of all of these proprietary data sets that banks use. So this is a famous data set. And that's what our example will be based off of here. All the other, one of the things this notes says right here is that all of these subsequent steps in this machine learning pipeline are all standard, doesn't actually depend in any way on how you load the data. And so if you wanted to, in the future, say in your capstone projects or something else, analyze some data set using some of the techniques from this class, you could just take this file, change line 29 right here to load your data instead of this data, and then everything else in this file would apply. Nothing special would have to happen. Okay, so loading the data, not a super interesting thing. For your purposes for the exam, the interesting part will be the shape of the data right here, the shape telling you how many dimensions, and so the D value and the N value. So this tells you the D value and the number of data points. Step 2 down here, apply non-learned data transformations. So we've talked about a handful of these non-learned data transformations in class. And I just have them all basically listed right here. So one-hot encoding any categorical columns. This German credit data does have a number of these categorical columns. We talked about them when we talked about one-hot encoding. That was our example. And it turns out this incantation right here does one-hot encoding. Handful of other, let's see, we haven't specifically talked about this, but a lot of the columns have like true or false as their values. This converts them to ones and zeros, numeric values, so that they can be used on our machine learning algorithms. Polynomial feature map has a convenient implementation here in scikit-learn, and same for the random projection has a convenient implementation right here. For your exam, the problem will steps 0 and 1 up here. These will all be exactly the same. Part 2 right here, step 2 is where the things will start getting different, in that I will select some subset of these feature transformations for you to have to deal with on your final exam. And you will have to be able to reason through, okay, what is the new VC dimension of these feature transformations based on whatever it is I give you. So in this case, the important parts here are the categorical will be increasing the VC dimension, the polynomial feature map here also increasing it, but then the random projection shrinking it back down. And you'll have to be able to understand just from these values that are placed here in the code, what the VC dimension is going to be. In this case, it's nice and easy because we have the random projection as the very last of these feature transformations. And so the in components right here, this is our output VC dimension right here of 120. It's not guaranteed, however, that the random projection, if it's included, will be the last one. The random projection could happen before the polynomial feature map, for example. And if that's the case, then there'll be a little bit more computation that you'll have to do to work through what the VC dimension is. One thing that will not happen is, so here I have 4 different feature transformations listed. I will not come up with like a 5th feature transformation that's not listed right here and throw that at you. So the things that you are responsible for are all contained in this step 2 section right here. And then step 3, creating the training and testing and also validation sets. This is what we're going to be continuing talking about with that last notes packet about why we need this validation set. The main takeaway from this step 3 is that we'll have 4 different data sets that we'll be working with. This training not, which is our full training set, a test set, and then a training without a 0 at the end, which will be our smaller training set and the validation set. And we started talking about those details last time, but we'll continue talking about those details today after we talk about the format of this exam. But the important thing that's going to happen going forward in this file right here is that all of our training is going to happen on this xtrain and our evaluation will happen on this xvalidate. But this set of code right here, step 3 is all going to be fixed. I'm not going to change any of this for you in the exam. Okay. Step 4, another interesting section which will be different for you on the exam than what's listed here. This is another set of data transformations. So again, these are the feature maps or the feature kernels that can be applied to the data. And here I have 1, 2, 3, 4, another 4 different types of feature transformations that can be applied. These ones are all, I'm calling them learned data transformations as opposed to the previous ones. And there's 2 things about them that make these learned data transformations. Syntactically, what makes them different from the previous ones is all of the feature transformations down here have a .fit function. So all of these feature transformations have the .fit function. That's what makes them learned, because we are somehow fitting what we're doing to the data. And so this standard scalar right here, this is, we've talked about it mathematically, although we haven't talked about the scikit-learn code right here. But the with mean right here and the with std, this is, should we do mean centering of the data, or should we divide by the standard deviation of the data, each of the data points? And so we talked about how that affects your VC dimension, which is that it does not affect it at all. And so this is a transformation right here that could possibly affect our in-sample error, but is not going to affect our generalization. And there are 4 of these types of, well, maybe, so why does this have a call to fit right here? Is because in order to center the data point, in order to center the data points, we need to actually calculate the mean of those data points. And that's different than, say, the polynomial feature map, where we don't need to calculate the mean of those data points. So this all has to happen after we've created our training data set. So these learned data transformations happen after we create the training data set. And again, there's 4 of these that you are responsible for. We've at least in passing mentioned all of them, but not talked about the scikit-learn implementation of most of these. And so you'll have to say, just look up the max absolute scalar right here and see what it is. And from the scikit-learn documentation, understand how it affects the VC dimension of the model. All of these learned from the data transformations, these are guaranteed to only appear in step 4 down here after the data sets have been created. The training test splits have been created. The step 2 transformations up here, these might appear either in step 2 or in step 4. So for example, this polynomial feature map, it could appear exactly where it's listed here in step 2, or it could also appear down here in step 4, say after standardizing the data. So any transformation from step 2 could also appear here. All of this up to this point is basically still the midterm 2 stuff, and just in a new format here. And this step 5 down here, actually training the model, is where we're getting into all the new stuff from the past month or so since midterm 2. And down here, I have, I think it's like 8 or 9, maybe 10 different models listed here. And you're responsible for all of these models and all of the hyperparameters that I have identified from these models. So for example, in logistic regression, we talked about how C is this regularization penalty. And so you're responsible for how changing C is going to affect our generalization error. Inside logistic regression, there are many other hyperparameters here that are much less important, and we haven't talked about them at all in class. And so you won't be responsible for any of those. You'll only be responsible for the ones that I've explicitly mentioned here. On the actual final exam, I will select one of these models, probably one of the more complicated ones like logistic regression or decision trees, and probably not a less complicated one like linear discriminant analysis, which has no hyperparameters. But I could select one of those, but I will select just one of these models, and that will be in your file for your final exam, and you'll have to tell me about that model in particular. Coming down here again, there's this validation accuracy. So this is going to be the performance of the model on just the validation set. Again, the validation set is the training set broken up into 2 halves, like a miniature training set and a miniature test set. And so this is our miniature test set, how we'll be evaluating your choices of hyperparameters on the exam. And again, the textbook, most of our discussions in class have been based around the error rate. So most of our discussions in class about error accuracy is just 1 minus the error. And so all of the things that we've talked about are equally valid for accuracy or error. You just have to sort of inverse the sign of everything to talk about the accuracy instead of the error. Different libraries, different people, different textbooks will talk about the accuracy or the error, and it's just understood that it's easy to go back and forth between the 2 of them. And so scikit-learn, for example, doesn't even have a built-in method of calculating the error. They only have a method of calculating the accuracy. Yeah, so your exam here, I will select one of these, and we will know what the actual accuracy on the validation set and the training set was, and based on that, you will have to, similar to your midterm 2 exam, you'll have to come up with a strategy for improving the performance of that model, either by adjusting the hyperparameters up here, or by changing what your feature maps are that you're applying before the data even gets to the model. Marco.
Are we only responsible for accuracy, or are we also responsible for, say, recall or precision?
The question is that there are many other ways that we could judge a model's quality that we haven't really talked about in class. We've only talked about error, which is equivalent to accuracy, but there are many other ways of measuring a model's capabilities as well. And for the exam here, you only need to know about accuracy versus error. Technically, all of the stuff that we have talked about in class is specific to just the error rate or the accuracy of a model. It generalizes exactly the same way that you would expect to other things that you might know about or heard about, like F1 score or precision recall. Those will all follow the exact same trends of like, if your VC dimension is too high and you're overfitting, then your error rate is too high. Your F1 score, which is more like accuracy than error, will be too low. And so fixing the error accuracy will also fix whatever those other metrics are.
Yeah, I might be mistaken, but I think you're missing two of the feature transformations on the file. I'm seeing 284. Maybe it's just on step 4. I'm only seeing 2.
It's very possible that I did not push to get. Let's see. I'll go ahead and let's see. I can't actually push it right now because I don't want to bring up my password while it's on Zoom. But I will definitely get that updated by right after class here. So the yeah, if there are things that I am missing, they will be added, and the whatever these notes that I'm taking in line right now will also be put on the repo. Thank you for pointing that out. Very last thing that's in this file is evaluating on the test set down here. And again, we'll talk about this test set versus validation set difference here in that last notes packet. But one of the important differences between the test set and the validation set is that the validation set we're allowed to look at more than once. So we're allowed to change our hyperparameters and optimize our model in different ways on the validation set up here. But this test set, we should only look at once. And so in theory, after we've optimized our model parameters, selected our model, decided what we're doing for transforming our features, then we could down here change this if false to if true and report the actual test accuracy as well. For the purposes of the final exam, this doesn't matter at all. The part that will matter is the portions up here. One last, I guess, mechanical detail that I will share here before I pause for more questions is these files, example1 and example2.py. They show you they are the same learning pipeline.py after I have done some of these modifications like I just described. So here, the apply non-learned data transformations. This particular example only has this convert non-numeric columns to numeric columns portion right here, and has no other feature transformations. And so that is an example of what you might see on the final exam. Step 3 here is all the same. Step 4 here, this one is only scaling the data and not doing anything else. And then this has just one model selected of logistic regression with these particular hyperparameters right here. So the example 1 and example 2, their purpose is just to make it clear exactly what the format of these the exam questions will be. I'm only giving you 2 of them because the purpose again is just to clarify the format, and it's very easy for you all to sort of create your own questions down here following that same procedure, the same way that I will be creating an individualized question for each of you, just picking one of these models down here to select and picking some set of combinations of feature transformations to select for your problem. Any questions about the mechanics of that? Yeah. In the same final folder, there's this example1.py and example2.py, and these 2 Python files are just the learning pipeline.py here, modified to be what an example like final exam would look like. Yeah, the question is, do you have to run these? The answer is you do not have to run these if you don't want to, but you are certainly welcome to run these to experiment with and try out different things. So these files are all valid Python files right now. They all are doing what they say they're doing. And if you run the default learning pipeline.py, will get a validation accuracy of 64% and a training accuracy of 71%. So we can see that it's just a little bit overfitting here, maybe. Yeah, on the final exam, you're not going to be sitting at your computer. It's just if you need those numbers, like especially at the very beginning of the problem, I will tell you what those numbers are, but we're not going to be like actually typing stuff on the computer to experiment with stuff. I will just tell you that you've made this change and that tell you what other numbers here that changed. Good question. Any other questions?
So will you be doing it on the computer when we make the changes, or are you just knowing all like what would happen?
Let's say you've proposed some changes, and I will not actually run those changes to say what the validation accuracy actually is. I will just make up a new number for you if it is important for you to make your decisions. That way we are not, I don't know. So this particular set of hyperparameters is relatively fast to run. Some of these combinations could take several hours to run. We don't want to be waiting in your final exam for several hours waiting for a program to finish. And we also don't want to, I don't know, have to be struggling over things like getting syntax correct in Python and wasting time with that. So we'll be focusing on just the big picture ideas, and me making up numbers will be to facilitate that for you all. But again, all of these, let's see, the vast majority of the various hyperparameters and feature maps and other things you're responsible here follow exactly what the theory predicts from our class here. There are some rare combinations, which you probably will not encounter, that we do not have a good understanding of yet. But so there are some things that might not exactly follow the predictions from class, but vast majority of things, almost certainly everything that you will encounter if you're just randomly playing around with different values here will follow the predictions of things that we talked about in class. And so you can say, for example, okay, I want to change my C value here to be a larger number, and go back to our notes on regularization. How does that make my affect my model? Well, the C is this like radius that the model is constrained to. So a larger C value means that we have a larger model. It's a superset of the smaller model, and so that's going to make my in-sample error go down, but very likely my generalization error will go up. And you will be able to observe things like that by changing these C values. Certainly any one of these parameters in isolation will follow all of our predictions in class. Okay.
Are we only tested on stuff in the notes or also stuff inside here?
Yeah, so the question is on exactly what is the extent of things that you need to know for the final exam. The the level 1 simplest answer here is that there are 60 of these hyperparameters that can be changed, and you have to be able to, for all 60 of those, know exactly how that's going to impact the various in-sample errors, generalization errors, runtimes, and so forth. And stated like that, that seems like a, I don't know, daunting task. That's a lot of things to memorize. But the vast majority of these, if you are understanding the general principles of, say, like for a decision tree, the VC dimension of the decision tree is proportional to the number of nodes, and then understanding how all of these affect the number of nodes of the tree, it becomes a little bit less daunting that way. In terms of Grading, in order to get a 100% on the exam, the expectation is that you would have basically all of the scikit-learn documentation about these parameters memorized and understood, and all of the different formulas in the notes packets memorized and understood. So that's, I don't know, maybe 20-ish different formulas about VC dimensions, and then these 60 parameters, how those affect those different formulas for VC dimensions. Does that answer your question? So it is definitely a lot of things here. But again, this is, so one of the reasons why we're doing this, many reasons why we're doing this, maybe the most immediate is on your, for data science majors or sequences, the capstone project will involve having a file exactly like this with a different data set being loaded in probably, but all of these same steps, and the clients want to have the maximum accuracy on their particular data set. And so you need to be able to work through all of these different transformations and things that you need to do. And then more concretely, if you all are trying to get a job as anything related to a machine learning or data mining, you will have to go through an interview where you are having to explain all of these different transformations to people on very likely data that you've never seen before that the company has using internally, and they'll have some sort of set of scikit-learn transformations or other libraries that they're using, and you'll have to be able to identify that, okay, the penalty here using L2 versus L1 regularization for this problem. L2 is the thing that makes sense because we're not trying to make our problem sparse. We're not trying to make our weights sparse. But the advantage of L1 is that it gives us a sparse output instead of a dense output. And you definitely have to be able to talk about that in an interview setting in order to get a job at all related to machine learning or data mining. Ava.
I know you kind of mentioned this, but just clarifying, we'll like receive the file, and do you want it, is it kind of like a password term where it's like a whiteboard conversation, or are we actually trying to evaluate?
It'll be a whiteboard conversation. So yeah, you're not at your computer coding things. It's just, I'll give you a printout. It'll be like 2 or 3 sheets with the appropriate parts in it. And I'll tell you, okay, here is my in-sample error, my training accuracy, and my validation accuracy. And based on those numbers, you will provide on the whiteboard your suggested plan to try to improve the performance. Margo?
Are we spending all 60 minutes on this, or are we also spending some time on page chart, let's say, or something like that?
Yeah, that's a good question. So zooming out a little bit about the rest of the exam. So let's come back here to the final exam README file. So we have our initial problem right here, talking about the learning pipeline. All of this is the material that we just talked about. And again, any of those print statements, like the accuracies, if you need those, I will provide them for you. And your first goal here is to provide a plan to improve the performance of that same model. You can expect a lot of follow-up questions about the particular model that we start with and the different hyperparameters, why you chose one hyperparameter over the other, for example, to change. After we've talked about that for 10 to 20 minutes, then we will have other follow-up questions about other models. You can expect at least one follow-up question about every one of the models listed there. So even if we start, say, on the k-nearest neighbors classifier, then we won't just stop there. We will also talk about the support vector machine and random forest and AdaBoost and all of these other things. I will ask at least one thing. You'll have to talk about at least all of these classifiers here at least once. So again, you should know the effect of all of those hyperparameters on both the runtime and the various statistical properties. You should also know the typical ranges for all of those hyperparameters. We talked about that in class for some of them, not all of them, not most of them. But the scikit-learn documentation will have reasonable values for all of them that you can look through. Depending on what we talk about in these follow-up questions in the initial problem will depend on exactly how we do review questions from the second midterm. And also, again, I have the notes about all the different things that you all individually missed from the second midterm. So I will focus the directions in that vein. And then for PageRank, I've decided to simplify things, and we will not explicitly cover PageRank on the final exam, so you don't have to stress out about reviewing your exponentially accelerated power method. Why? I hear you all asking. Again, the main purpose of PageRank was to give us some initial exercise and understanding how to do the runtimes of these algorithms. And so I feel like that portion of the PageRank midterm is fully covered by talking about, say, stochastic gradient descent and the perceptron algorithm and gradient descent and the runtimes of all those algorithms. And PageRank's also material that you definitely will not be explicitly asked in an interview session. Nobody will ever ask you in an interview what is the PageRank formula, or what is a stochastic matrix. That won't come up. People might talk about PageRank at a higher level. But since it's not likely to be used directly in an interview setting, I wanted us to focus on the stuff that definitely will happen in interview. So all of this stuff here. And I guess I'm using interview as shorthand, both for interview and capstone situations. But because there is still, we're really covering all the important stuff about PageRank, about all those computational issues, your final exam score can still replace your first midterm score if your final exam score is higher. Also, if for whatever reason you did do poorly on the first midterm, you'd expect me to definitely ask questions, lots of questions about the runtime of things like gradient descent and stochastic gradient descent in the perceptron. So all of those concepts, matrix multiplication runtimes and so forth, getting covered in this portion here. Does that answer your question, Marco?
Yep.
Yes, Kate.
So that means that any topics that you missed on the first exam will not be discussed in the class again on the final?
True statement. So if you missed something on the first exam about, say, stochastic matrix and why it's important that the PageRank matrix be stochastic, or the difference between P bar and P bar bar, then that will not be explicitly asked on the final exam here. So you all can narrow down your studying efforts a little bit, maybe a lot of it. Yes.
Do you still have the records of what we missed on the first exam in case we want to ask you to no.
I still have everybody's sheets, so if for whatever reason you want to take a look at them, you can come to my office hours and I can pull it out and we can talk about it. All great questions. Any other questions about anything administrative or final exam? Maybe one last thing here then. Extra credit homework here at the very bottom. So you can get up to 4 points of extra credit for finding good hyperparameters for that German credit data set. So this is this problem here that is for our final exam. Finding these good hyperparameters means figuring out which of these feature transformations is a good feature transformation, and which model down here is a good model to use, and what the best hyperparameters should be for that model. And so my hope is that by playing around with those hyperparameters and trying to find good models, you will also be studying for the final exam, getting familiar with the data and the code base there. The way the grading will work is that if you get at least a 74% accuracy, you'll get 1 point. And then for each additional point of accuracy you get beyond that, you get 1 more point of extra credit there. So if you get 77% or above, then you will get all 4 of these extra credit points right here. In order to do this, so just the rules here, you can't modify any code in step 0, 1, or 3. So that's just like the data loading code. So you can't say just load a easier data set to solve the problem. I put this, you may collaborate with at most 1 person here. The intention about that is so that we don't just have 1 person who figures out the magical hyperparameters to get this and distributes it to the rest of the class. But I encourage you still to like do your studying for the exam with other people. It's definitely okay to say talk to other people about like, okay, if I'm using logistic regression here and I change my max iterations from 100 to 10, how is that going to affect my BC dimension? Which it will not. It's certainly okay to talk about those sorts of things with other people. And then to claim the extra credit in Sakai, you just submit these 3 things here to Sakai, and I will give you the extra credit. Due date for this is whatever your final exam date is. Yeah.
With the validation accuracy, is that when, because in the code you have it when you're doing it on the like, oh, so it's that one.
Yeah, so specifically here is what I am looking for.
Okay.
Yeah. Okay, good questions. Any last questions about anything related to the final? Everyone's excited for it, looking forward to your final. I'm sure nobody is dreading it or anything like that. Okay, then today, the rest of the time in class, we will probably finish up this validation model selection set of notes right here, chapter 4.3, our last set of notes from the textbook. And whether we finish it up or not, we'll definitely have it finished by Wednesday, and we'll spend most of the time on Wednesday doing just final exam preparation, going through practice problems, reviewing all of the previous stuff. It's been a lot of things that we've talked about over the last month. Easy to forget some of the highlights, important stuff from the first, from a month ago. Last time in class, we just did we started these notes, but did not get too far into them. Again, the high level idea why we're doing this set of notes now is that validation here or model selection is our technique for selecting which model we're going to use and what those correct hyperparameters are for us. And we talked about all of these different models in the Model Zoo section so that when we talked about model selection here, we would have a lot of examples to think about and choose from. Concretely, we have all of these examples in this file right here, thinking about we have all of these different models listed, all of these different hyperparameter combinations. There are 60 of these different things that can be set to different values, and different combinations of them do things in weird ways. So there are a very large number of models, things that we might want to try here. And the key idea, or the main place that we got to last time, is talking about this validation set and starting to talk about the notation here. The validation set, again, I'll back up first and say the train and the test sets are what the textbook originally used. It's what we've been using for chapters 1 through 3. Make sure that I'm not using the wrong set of notes. And actually just D by itself is the training set, not D with subscript train. The size of this data set right here, get that straightened up. The size of this data set right here is of size n, and the size of this data set right here was n subtest. And then the D data set, our original training data set, this is now being split into 2 halves, this D sub train and D sub val for validation. D sub train has size in minus k, and validation here has size k. And what we're going to be doing, what the code that we just looked at is doing, is it's training our models here only on this smaller training set right here, and validating our models here on this, this validation set. And we will, the big picture idea of this, the reason we do this is because statistically things work out nice to use this validation set many, many times, and then only use the test set exactly once. I'm going to scroll down a little bit here. The very last bullet point here says describe the difference between a test set and a validation set. The key difference here, this test set, again, used exactly once. Exactly one time. And the validation set used more than one time. But the principle behind them otherwise is the same. They're both used to estimate the E out of our problem, our out of sample error. Both used to estimate the out of sample error, E sub out. Scrolling back up here a little bit, there's two additional pieces of notation right here that the textbook introduces. And the idea behind all of this notation, I think, is really straightforward. But the notation itself gets really awkward really quickly with a lot of different subscripts and superscripts around to track all the different data sets. So if you can get over the intimidation of the notation, then the ideas are hopefully pretty straightforward. So previously, our G all by itself, this was our empirical risk minimizer. This is our hypothesis trained on the data. Now, instead of G, they're introducing this new notation G minus. This minus sign right here is supposed to be indicative that we're not trained on all the data. We're trained on only a small portion of the data, like something has been subtracted from our data. And so G minus is trained on dtrain and evaluated on dval. So the minus, anytime in this section you see the minus associated with a hypothesis, it means that it is using this like blue training validation set split right here to do the training and evaluation, rather than the red training test split that we've been talking about in the past. That's one new notation. The next new notation is they introduce this idea of eval. This is the error rate on the validation set. And the, if you think about, or if you tried to guess what it would be based on our other measures, our other variables that are E sub something, it'll look very similar. So the eval starts off as 1 over k times the sum here. Again, the 1 over k coming from the fact that we're going to be summing over all of these data points in the validation data set right here and averaging them. So 1 over k right here. Whereas our in-sample error was 1 over the big N up here. Our e-test was 1 over n-test over here. So 1 over k times the sum of x sub n contained in dval. So looping over every data point in our validation set right here. And then the notation here is a little bit different than from what we've talked about in class, only because it's they're doing just the most general version of the notation and not skipping to all the intermediate steps that we talked about. It looks like E of G minus of X, comma, Y sub N, like this. And here, this E sub n, this is our loss function. This E right here, that's our loss function. So previously, the textbook, and we used the script L like this, and for whatever reason, they're changing to E right here, E standing for error. And so typically, the 0-1 loss is the thing that we would be caring about here, or the accuracy, but they're being generic to accommodate any different loss function right here. Yes.
This loss, like basically the number of like misclassified.
So yeah, so the question is, what exact loss function are we using? And they wrote it out generically here, where it could be anything, but the one that's always used is the 0-1 loss, which is the number of misclassified points. So I'll write that out. Do what color? Go gray. Usually 0-1 loss, which is number of misclassified points. One of the many difficult things about data mining, but one of the things that's more difficult than it really should be is that there's just so much different notation that's used in different ways, and so many levels of genericness that the notation can be expressed in, and it just takes a lot of time, seeing all of those different levels of genericness in different situations to get comfortable with that. But this would be the standard way that most people would talk about it. Most practitioners normally talking about these equations in the most generic way. Good question. Okay, so why do we care about this notation? The main purpose for us so far is to get to this equation right here. This is one of those equations that to get 100% on the final exam, you definitely need to know, and I want to say memorize, but memorize is not quite the right word, because if you understand all of the things that we've talked about in class, then this equation becomes fully obvious, all of these relationships right here. And so as you're studying, you want to be able to find these connections that help make equations like this become obvious, and not just something that's has to be memorized totally out of the blue. So why is this, or what is this equation saying, first of all? So our out-of-sample error on G, our out-of-sample error on the hypothesis trained on the entire training set, that is going to be less than or equal to the out-of-sample error on G minus, again, the hypothesis trained on this smaller minus data set. Why is that going to be the case? Well, this follows from our VC dimension bounds, where this portion right here, this is equal to En plus the O of square root. And I'm going to save myself some notation, make this a little bit cleaner, just say that all of this is in big O notation, all asymptotic notation down here, all in big O down here. So En plus the square root of dVC divided by N. Whereas our G minus, the out of sample error here is going to be worse because it's trained on less data. So our E out right here is now going to be En plus the square root of dVC over N minus K right here. And if K is small, then these two quantities will be very close to each other. But because K is going to be some non-negative number, some positive number, this quantity on the right-hand side is going to be worse than this quantity here on the left-hand side. This quantity right here will be larger than this quantity right here. Another sort of subtlety about these equations is that this is all with high probability or in expectation, because again, they're there are these plus the log of delta terms over here, where the delta is the probability. And so all of these quantities are with high probability. So I said right here, they're all in big O. They're also all with high probability. Let's see. So those are the relationships between E out of G and E out of G minus. Then the relationship between E out of G minus and the validation set here, this is the same relationship that we have about the Hoeffding inequality from D over here to D test. The same relationship from D to D test exists between D train and D val with the Hoeffding inequality. And so this follows from Hoeffding right here. And again, this K over here, this is the size of the validation set. And so that is the, however big our validation set is, that is what defines the bound, how the goodness of our validation set as a representation of our out of sample error over here. At this point, there's a lot of notation without a whole lot of benefit. The next page is where the benefit's going to come from.
So when we're comparing the G to G minus, are we talking about the bounds or the values?
So G here is a function. So like G itself can't be compared
It's like
with,
E out.
but the out of sample error here, we are talking about, yeah, so this is an informal equation right here, because these are all like with high probability that yeah, so it's not guaranteed to hold, but hold with high probability. I don't think that's quite what your question was, though. Your question about was like, is this just about the bounds, or is this like more fundamental than those bounds? And it turns out that the bounds that we have are strictly tight, and you can't do better than them. So there's no distinction between like, is this inequality about the bounds, or is it about the actual value itself, because of that tightness. But either way to think about it is will get you all the correct reasoning. Yeah, I'm sure. Let's see. I'm gonna hold questions for a couple seconds to talk about the next page. The next page gets into the why do we care. We just need to introduce a little bit more notation before we get to the why do we care. And once we do that, that will maybe make some things here hopefully click a little bit more. So again, yeah, this is section 4.3 for the 0.1 from the textbook, just introducing a whole bunch of notation about this validation set. Section 4.3.2, getting into the why do we actually care part here. And the reason that we care is because, so I'll do it at a high level intuition and then get into the notation. At a high level intuition, this Hoeffding inequality, one of the things that we talked about is Hoeffding is only valid if all the data points are exactly independent of each other. If the data points depend on each other in any way, then the Hoeffding inequality can no longer be applied. And it turns out that if you apply multiple models, like if you do multiple experiments with your training set to measure their validation accuracy, then those experiments are no longer independent of each other. And the purpose of this validation set is to account for that lack of independence of each other. And so we'll formalize that now with the notation here in 4.3.2. The first thing that they introduce here is this idea of a validation hypothesis class, H sub val. And this is equal to, the way they define it, G1 minus, comma, G2 minus, comma, dot, 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 comma, G sub n minus, like this. Each one of these hypotheses right here, this is an individual model trained on, so this is an individual model that has some combination of hyperparameters that has been trained on our smaller training data set, which is that D sub train. In code, one way to think about this is, I'm going to switch over back to the code for a second. I'll come back here in a minute. In code, each one of those G minuses is like one of these models right here, where one G minus could be logistic regression with all of these hyperparameters. The next G minus could be SGD classifier with these hyperparameters. A third G minus could be a different SGD classifier with a different set of hyperparameters. But so each one of those G minus sub i's is one of these models right here that is being evaluated on this validation set right here. And if we do that, if we evaluate those models, one way of thinking about that is that we had some finite hypothesis class, this H sub val, that had a finite number of models inside of it. These are all of the models that we've actually tried. And so these are all the models that we actually try. These are all the models we actually try. So as you're working on, say, that extra credit homework assignment, all of the different trials that you're doing, those are all individually one of these G sub i's over here. And this in value, however many entries there are, that's the total number of times. Total number of times that you try something, that you try a different model hyperparameter combination, that you try a model. And again, this H sub val right here, this is a finite hypothesis class. Each one of these individual hypotheses that we have contained in this set, these might come from infinite hypothesis classes over here. These might come from infinite hypothesis classes, but H-val itself is just a finite hypothesis class. And the idea is that the final model that we want to use is the model that does the best over here on the validation set. And we can use that finite hypothesis class generalization theorem in order to see how good that bound is going to be on our test set. So, sorry, one last set of notation here. This G minus M sub star. It's the same model that's being placed down here. G minus M sub star is the this is the best of the models in the H-val hypothesis class down here. So the argmin over G minus contained in H-val of E-val Gi sub minus. So this G minus M sub star, this is the best possible model on this finite hypothesis class right here. Best possible model on the finite hypothesis class. And because it's a finite hypothesis class, we have this generalization bound right here. This comes from the finite hypothesis class generalization theorem. Finite hypothesis class generalization theorem. Okay, I'll pause for questions. One question that I hear all of you screaming to ask is like, how many models can I try on this validation set and still have things make sense? Like if I have k equals 1,000, so I have 1,000 data points in my validation set, does that mean I'm only allowed 1,000 trials of different hyperparameters, or less than 1,000, or more than 1,000? And the answer is that because we have this log factor right here, this log factor in the numerator right here, we can try a lot of model combinations. So for whatever our K size is, whatever our validation set size is, this equation over here is grows linear in the size of K, but it's logarithmic in the size of M. So K definitely dominates over here, and you can do a lot of experiments without this term blowing up too much. Okay.
What is a good K to N ratio?
Yeah, so the question is, like, in practice, what is a good like K to M ratio? And the answer is that K to N ratio. Yeah, so the what are like good sizes of these training test validation sets? That's a decision that you have to make. The choices that I made up here in our the step 3, create train test sets right here. Nobody would think it's weird if you chose this for any problem. This is a good standard size to use. For some situations, people will like dive into the actual like constant factors of their the Hufting inequality to determine exactly how many data points they need if they are really like data set restricted somehow. But this is a pretty standard set to use right here. So one thing you'll notice here is that the validation set is just a little bit larger than the test set. The validation set here is just a little bit larger than the test set. One reason for that is because in our validation accuracy over here, we have this log M in the numerator. But in our test set, because we're using our test set exactly once, there's only a 1 in the numerator over here instead of a log M in the numerator. So that's standard practice to have your validation set be just a little bit larger than your test set for that reason. Yeah, there's, in terms of like, yeah, the training set size versus the test set and validation size, that's something that you would have to break out the Hufting inequality to get your actual like confidence bound what that tells us. But this is a pretty standard sort of breakdown. Okay.
I'm still confused on like why we created the validation set and what I was talking back to like how we got to the generalization error from the Hufting inequality. Like we added an extra M to factor for like the M different hypotheses. Is that like why we like try to create a bound between the bound and the out now instead of leaving the out to get rid of the M?
Yeah, let's see. So the question about like, why do we have this validation set? And the answer is that without the validation set, we can't actually say anything about the training set if we look at the training set more than once, or sorry, if we look at the test set more than once. The Hufting inequality that we talked about for midterm 2, about how that tells us information about the test set, that assumes that we only look at the test set exactly once. And in practice, we want to look at somehow measure the result of our model many times in order to determine which hyperparameters are going to be better. And so in order to do that, we have to have the validation set. Without the validation set, if we look at our test set more than once, we can't say anything about the test set.
Are we training on multiple times?
Question is, are we training on the test set multiple times? And the answer is you're not explicitly training on the test set, but if you look at the test set and make a decision based on that, then you are in fact somehow training on it, even though it's not like an explicit function call that trains on the test set. You've made a decision somehow on the test set. And our theory requires us that we make no decisions at all based on the test set. The purpose of this validation set is that it allows us to make some decisions about that. So we just have a couple minutes left, and there's a fun story here that I want to share with you all. If people still have more questions about things after the story here, I'll take those after class. But I want to talk about this story. So in 2015, this was the very beginning of the deep learning era, which started in most people count it as 2014. And Baidu Research, so this is like the Google of China. Was at the time a very prominent, still very prominent machine learning research company. But at the time they were acquiring a lot of talent from like Google and Facebook and importing them into China. Andrew Ng here being one of the most famous. He was a Stanford professor, foundational in a lot of different things that we've talked about here in class. And he went over to lead Baidu Research for a while. But his team at Baidu Research was accused of cheating on this ImageNet dataset that we talked about for your fine-tuning homework assignment. So the ImageNet dataset is the one that they trained those original feature maps on. And this link tells us the details. So going over to that link, here is the main plot of that the contest organizers used to uncover this cheating and eventually get this person, Wen Ru, fired from his job at Baidu, and he is not allowed to work in the machine learning industry these days. Nobody wants to hire him because of this cheating scandal. But what happened was that on this ImageNet challenge, there was a specific set of numbers of times, a number of times that you were allowed to do hyperparameter optimization to submit your model to the server in order for the server to say what your accuracy score was. And the reason for that specific number was so that this log m term up here would be bounded and the validation scores that were being reported for each team would be roughly equivalent to each other. But he cheated by creating multiple accounts on this server and submitting validation tests under all of those different accounts. And so his log m factor over here was about 10 times higher than everybody else's. And so even though he got the best actual results because of these, or the best number on the validation set, because of this bound right here, we can't trust his results as actually being better. And so what's these dots are all of his different models, each of those G sub i's that he submitted to the test server. And these circled regions are what they call these hyperparameter optimizations, where he selected many different values of something like the C value here, for example, and wanted to try all those different values to see which one worked the best. And these successful hyperparameter optimizations, you can see he chose a parameter that actually did impact performance a lot, and then so went with whatever was the best one. This red circle right here, he chose one that didn't matter at all, and so it all stayed the same. But so if you're interested in why people care about this, it will cause, if you do it incorrectly, you to lose your job and lots of people to hate you. I don't feel too bad about making fun or highlighting the fact that Wen Ru cannot work in industry ever again, because while he was working there, he was making over $1 million a year. And so the fact that he can't work ever again is, I don't know, not super important to him. That's it for, there's some more, oh yeah, a little bit more that we'll talk about on Wednesday. We'll mostly cover, do a review for the final exam though on Wednesday. If you all have any other questions about anything, happy to stick around and get those answered today. Or again, there's the office hours on Tuesday and lots of review sessions this week.